What's up guys, it's Imran Fiaz and today's video is on AQA Level Chemistry Paper 3 2017. Just Section 8, multiple choice questions I'll probably go through in a different video or tomorrow. Suggest one reason why the enthalpy change for this reaction cannot be determined directly by calorimetry. The idea that not possible to prevent some dissolving. It's not possible to prevent some dissolving. Question 1.2. Calculate enthalpy change for the absorption of water by magnesium chloride to form that. Absorption of water. Enthalpy change. I'm given this. And I know from the equation here that's that. That's that, right? And I'm going to calculate enthalpy change. So it's going to be basically, it's going to be minus 155 minus 39. So minus 155 plus 39, which is minus 116, because we can multiply minus 1. And that's again using creating cycles and being able to do that as well. 1.3, describe how you carried out experiment to determine the enthalpy solution of this. 6 marker practical already. Question, third part of the question. So the first thing I want to do is the method, right? Stage 1, the method. Measure water with a beaker. At a suitable volume, add mass 10 grams into an insulated container, add known mass of magnesium chloride solid, use of before and after weighing method. Stage 2, measurements. The idea, we record the initial temperature for 2 minutes, record temperature at regular timed intervals for 5+ minutes, and then plot t versus time. And then stage 3, the use of results. Explain how your results could be used to calculate enthalpy of solution. The idea, we want to extrapolate both lines to when solid added. So to when solid added, to find initial and final temperature, and that's enthalpy change. And then we use Q, and obviously T final minus T initial equals your temperature change, and then use Q equals MC delta T, then use moles equals mass over mR, and then you can find finally your enthalpy of solution, which in this case is going to be, because I know that enthalpy change is negative, so I know the temperature increases, right? So it's going to be delta H of solution is going to be minus Q divided by 8.39 times my 10 to the power minus 3, and that's just moles. And how do I get the moles? It's just going to be 0.8 over the mol. Right, 95.3 of anhydrous magnesium chloride. Question 1.4. It says, uses data to plot a free energy graph of this against temperature, the grid opposite, and calculate the gradient and hence calculate entropy change. So these type of questions are becoming more and more common, where it's not asking you to calculate entropy change or anything or give you energy change. It's giving you a graph. It wants you to plot the graph and then use the graph to find out your answer. So first thing you do is, it's already giving you this, you just plot the graph very simply, and what you should notice is that you get like a straight line. Obviously that's not accurate, but this from mark scheme. But anyway, the main thing is, because it's a straight line graph, y equals mx plus c, right? And I know Gibbs energy change is delta G equals delta H minus T delta S, right? Therefore, delta G equals minus T delta S plus delta H. So now you can see, sort of compare what you're working with, right? So I know what's the gradient? The gradient is delta S, X is minus T. So the gradient is, minus delta S. That's what it is. And show that comparing, and then I'll say gradient is minus delta S, and then just find out the gradient. Find out the gradient, and then that's minus delta S, and divide by minus 1. Delta S is minus 167, because it's more joules k to the power minus 1 multiplied by minus 1. 5 marks for that. You just have to plot your graph, then compare it, find your gradient, and then and also a thing I skipped is that because delta G is kilojoules per mole to power minus 1, you'll get your gradient as 0.167. Therefore delta S is minus 0.167. Therefore I want it in joules k to power minus 1, so I do need to times by 1000. That's always a trick they like to include, so don't fall for that as well. Question 2.1, name the mechanism for the reaction of concentrated sulfuric acid with alkene. It's obviously going to be electrophilic addition. Year 1 mechanism, showing you guys that, testing any content from year 1, year 2. Outline the mechanism for the reaction of concentrated sulfuric acid with propene to show the formation of the major product. So first thing I would do is propene, so carbon-carbon double bond, hydrogen, right? You've got a CH3 group here, and you've got a hydrogen here. Concentrated sulfuric acid, hydrogen partially positive, oxygen partially negative, S double bond O, OH. Curly arrow from the double bond to here. Then you go here, and this is just using my knowledge of the mechanism, right? The major product and the minor product, I'll come to that in a second. You should get this. Hydrogen here, CH3 here. Formation of the major product, so I want it to be attached to here, this carbon, right? Because that will be then a secondary alcohol. No, a secondary, you know what I mean. It would be the major product. So the hydrogen has to be here, carbon cation here, positive charge. Then the oxygen with a lone pair of electrons, a negative charge. S double bond O, OH, and then it bonds to here, and then you form this hydrogen and O S double bond O, OH, CH3, and there you go. That is your major product. Let's check the mole scheme. See that hydrogen there, CH3 on the left, and CH3 on the right. Perfect. Now that's a major product. And then it said George Washington minor product. That's going to be a very nice one marker because the minor product therefore is going to be when it's attached to this carbon instead. So it's just going to be this. First I draw it out like that. The methyl group is here. And instead of, the carbocation being on the second carbon, it's going to be here. But obviously it just wants the structure, so I don't need to go through all of that. It's just going to be the OS double bond OH. Double bond OH. And there you go. CH3, CH2, CH2O, SO3OH. Explain why the product shown in the answer to question 2.2 is a major product. Classic question, classic question. Major product formed via more stable carbocation due to electron releasing character / positive inductive effect of two alkyl groups compared to one. Major product formed by a more stable carbocation due to electron releasing character / positive inductive effect of two alkyl groups compared to one. Okay, this one says butane 2-ol reacts with concentrated sulfuric acid, to form a mixture of three alkenes. Two of the alkenes are stereoisomers. Draw the discrete formula of each of the three isomeric alkenes named by the reaction formed by the reaction of butane 2-ol concentrated sulfuric acid. Give the full IUPAC name of each isomer. So first thing I would go through is what mechanism is it between butane 2-ol and concentrated sulfuric acid to form an alkene? Well, it's alcohol. I'm reacting it with concentrated sulfuric acid to get my alkene. So alcohol, it's gonna be what's it called? Elimination of water from some dehydration reaction. So the one that I go through in my playlist of mechanisms, elimination of water from ethanol to form ethene. So elimination of this to form that. So I know I'm gonna form that. Now I'm gonna actually go through the mechanism: butane 2-ol, methane, ethane, propane, butane 2-ol, and then I've got concentrated sulfuric acid. Double bond OH. What happens is oxygen has a lone pair of electrons and then goes to here, right? Lone pair of electrons, bonds to here. So I'm going to form bute, either 1-ene, 2-ene, or 3-ene, and I can see that from here. So bute 1-ene, the skeletal formula, okay. So methane, ethane, propane, butane, 1, 2, 3, 4, bute 1-ene, so that bute dash 1-ene. Oh yeah, and the name bute dash 1-ene dash 1 dash E. The second one, there you go. I'll actually put it here instead, and that's obviously going to be E-bute 2-ene because the enemy is these two. So E-bute 2-ene, and the final one is, instead of that, it just goes like this, and you've got this here. So that's Z bute 2-ene. So bute 1-ene, E bute 2-ene, Z bute 2-ene. And obviously you can't have bute 3-ene because then it's just completely symmetrical anyway. A byproduct of the reaction of butane 2-ol with concentrated sulfuric acid is molecular formula. C4H8O. Name this byproduct. Identify the role of sulfuric acid in its formation. Suggests the name of method used to separate products of this reaction. So it's testing a lot of content in this question. So name the byproduct of name this. So C4H8O. So that's obviously going to be butanone ketone. So butanone. That's not too difficult. Butanone. The role of sulfuric acid in its formation. So I'm reaction of butanol. So I'm reaction with an alcohol with concentrated sulfuric acid to form an aldehyde. So alcohol to aldehyde is going to be an oxidizing agent. The role of sulfuric acid, the oxidizing agent. Name of separation method, fractional distillation. Concentrated sulfuric acid reacts with solid sodium chloride. Give the observation you're making this in this reaction. State role of sulfuric acid. Now I know sulfuric acid, its role in this case is a base. Actually, no, it's not. It's proton donor. Proton donor. The observation, white fumes. White misty fumes, whatever you want to say. White misty fumes. And it just shows you how you also need to know the observations as well, because I thought it was going to ask you give the equation, but it doesn't. And then it says concentrated sulfuric acid reacts with solid sodium iodide to produce several products. Observations made during this reaction included the formation of a black solid, a yellow solid, and a gas with the smell of bad eggs. Now I know already, because you do need to know these reactions, all of that. That's H2S, the yellow solid and the black solid. So with concentrated sulfuric acid with solid sodium iodide, I'm going to go through the equation so you guys know what I'm going on about. So it first starts with sodium iodide plus H2SO4, and what you form is NaHSO4 plus HI, right? Then what happens is then you got 2HI plus H2SO4 to form what is it called again? I know you form, I think you form I2 plus SO2 plus 2H12. And is that balanced? Yes, it is. And then the third one, you get 6HI plus SO2 to form I2, but in this case it's going to be 3I2 plus H2S, which I know I'm going to form, plus 3H2O. No, it's going to be 2H2O because it balances out. Okay, let me just double check that equation is correct, because I just recalled that all off by memory, so I could be incorrect. So let's go through that. So first one is correct, first equation. Then yep, that's correct, second one, and then third one is also correct. Perfect. So then now I've shown you guys the equation. The gas that smells bad like H2S, the black solid is going to be I2, iodine. The yellow solid, well, what else will I form? SO2. but the actual thing that gives the yellow solid is S. Okay, it says so I2S H2S. Suggest how the anti-bumping granules prevent bumping during reflux. Prevents the formation of larger bubbles. Classic one marker prevents the formation, alhamdulillah, of larger bubbles. Show by calculation that an excess sodium hydroxide is used in this reaction. So there's a lot of information, but it says benzoic acid can be prepared from ether benzoate. First hydrolyzed, added this much ether benzoate to this much of aqueous sodium hydroxide round bottom flask. I want to show that excess sodium hydroxide is used in this equation. So first thing I'm going to do is add 5 centimeters cube of ether benzoate to this much to 30 centimeters cube of aqueous 2 moles. So first thing I'm going to do is I'm going to calculate the moles of sodium hydroxide. And don't be fooled that it's 2 marks, so it's going to be like, it's not going to be that many steps. So moles of sodium hydroxide, 30 divided by 1000 times by 2. And then what I'm going to do is I'm going to find out the moles of the ester. Moles of ester. Moles of ester, which is going to be, I know the density is mass over volume. Therefore, mass is density times by volume. Therefore, it's going to be 1.05 times by 5. 1.05 times by 5 divided by the MR, which is 150. Perfect. And then you just compare it. So you get moles of the ester as 0.035 moles, the moles of sodium hydroxide 0.06 moles. And there you've shown it's in excess, significantly larger than the ester. And it just says show by calculation. You don't need to do anything else, just show your calculation. Suggest when excess of sodium hydroxide is used to ensure all the ester reacts. To ensure all the ester reacts. Suggest when an electric heater is used while the Bunsen burner flame in this hydrolysis. Ethanol is flammable. State why reflux is used in this hydrolysis. Reflux allows reactant vapors to be returned to the reaction mixture. Or you could say, or reflux does not allow any reactant vapor to escape. Write an equation for the reaction between sodium benzoate and hydrochloric acid. Now hydrochloric acid is obviously going to be HCl. Sodium benzoate, well, first thing I'm going to do, well, sodium benzoate, so carboxylate, and I've got benzene, I've got sodium, so it's going to be C6H5, first things first, then carboxylate, COO, but sodium as well. So there you go, C6H5, COO, Na plus HCl, and then what you form is C6H5, COOH plus NaCl. Suggest why sodium benzoate is soluble in cold water, but benzoic acid is insoluble in cold water. The idea that sodium benzoate is ionic, hence soluble in cold water, whereas benzoic acid is insoluble as despite polarity of COOH group, benzene ring is non-polar. Question 3 point, after the solid benzoic acid has been filtered, it can be purified. Describe method to purify the benzoic acid. Again, this is a practical skill you just have to memorize. So dissolve crude product in hot solvent of minimum volume, filter to remove insoluble impurities, cool to recrystallize, filter under reduced pressure with a Buchner funnel, and then wash with cold solvent and dry. Cold solvent to remove impurities from the surface. Again, you know, 2 practical questions already, both 6 marks, I think. Yeah, the first one was 6 marks. It was, yeah, that's already 12 marks. Since if you haven't gone through the practicals, you lost 12 marks already. Question 3.9 is similar experiment. Another student used this much moles of ethyl benzoate and obtained this much of benzoic acid. Calculate percentage yield of benzoic acid. So percentage yield of benzoic acid, first thing I need to do is calculate the moles. Well, first thing I'll do is ethyl benzoate and benzoic acid. Let's go back to the equation. Ethyl benzoate and benzoic acid. What's benzoic acid? Benzoic acid. And then, so I can see here that if I find out the moles of, benzoic acid, which is 5.12. Now the MR is going to be a problem because has it given me the MR of benzoic acid? No, it hasn't. Benzoic acid. So it's going to be a C6H5, 12 times by 6 plus 5 plus 12 plus 16 plus 16. Plus 1. So it's going to be 1 to 2. Then I get the moles as 0.042. Then to calculate percentage of benzoic acid, I'm going to do 0.040. No, sorry, no. 0.042, because that's how I obtained this much. So 0.042 over 0.040 times by 100, 105%. Then it says suggest why the yield is not 100%. The idea the product is not dried / impurities present in the product. Question 4 says suggest a pH range of a suitable indicator for this titration. So pH range, I go look at here, right? Halfway, somewhere around about 9, right? Suggest a pH range, I'd say, because it's a range, anything really between this part, so 7 to 10. 7 to 10. Give the expression for the acid dissociation constant of Hx. It's going to be, well, I've got Hx at the bottom, and then I've got H plus, X minus. And remember, square brackets. Don't forget square brackets. Calculate the constitution of Hx in the original solution. So I know Ka is that, and I want to find out the concentration of Hx in the original solution. I want to find out the concentration of this in the original solution. So what I'm going to do first is rearrange it. So I get Hx equals H plus X minus divided by Ka. I know Ka. Let's do that. 0.10 times by. So first thing I would do, I can see you've got sodium hydroxide. So um, calculate concentration of HX in the original solution, and it says this much solution of sodium hydroxide gradually added to this much of weak acid. So the moles of HX and the moles of sodium hydroxide equals what? What's it going to equal to? Well, it's going to be 24 O divided by 1000. That would give me the moles, 2.4 times by 10 to the power minus 3. So I'm using moles as concentration times by volume. Yeah, and then I get the moles. And then to find out the concentration of HX, moles, concentration, volume, concentration moles, which I just worked out, divided by the volume of HX, which is the weak acid HX, 25 divided by 1000. And you should get 0.0960 moles per DM minus cubed. Calculate pH of solution before the addition of any sodium hydroxide. So before sodium hydroxide was added. Well, I know Ka equals concentration of H plus squared then divided by HA. And I've got the concentration of that. So the concentration of H plus or HX I should say, but it's fine. 0.0960. Then to find out the concentration of H plus is going to be the square root of Ka 2.62 times by 10 to the power minus 5 times by 0.0960, and left to find a pH. Well, pH equals minus log 10 concentration H plus, and I just substitute that answer in, and I get 2.80. Calculate pH of solution when half of the acid had reacted. Now this one is a tricky question. Just testing, do you know that skill, that the idea that when half of the acid had reacted, half neutralization. Half neutralization. So if it's half neutralization, what's the key fact? That pH at half neutralization equals pKa. And what is pKa? Well, Ka equals 10 to the power minus pKa. What's pKa? pKa equals minus log 10 of Ka. Therefore, if I find out pKa, that's the same as pH. So, minus log 10, 2.62 times by 10 to the power minus 5, and I get 4.58. And since it's pH, it must be 2 decimal places. So that's a trick, right? Half the acid reactive, so you need to understand your half neutralization. pK is minus log 10 Ka. Once you got pK, you've got pH. Apply your answers to questions 4.4 and 4.5 in the grid. pH of HX 2.80. That's when, before the addition of any sodium hydroxide. So before, so that's when it's 0, right? So that should be here, never mind. And the other one, 4.5, calculate pH when half of the acid had reacted. Half of the acid had reacted. Half of the acid had reacted. Yeah. 25 centimeters cube of weak acid HX, so half of it, so 12.5 then. And then plot your point there. And that is the end of section A.